Light bulb. Hey, how many watt is this bulb?
60.
Again,
40.
40 probably. Again, 73.
Point.
40, 60, 75, or 100.
You have a 60?
40?
Can I have it? My light bulb in my room.
Hold on.
2 weeks.
2 weeks?
Yeah.
All right, now look.
Yeah, it is 40.
Okay, you all fail. How many watt light bulb is this?
However many it needs to be.
I don't know. It says it on there.
How many light bulbs is it?
How many watt light bulb is this?
It's a one light bulb.
What? Light bulb?
0 right now.
There you go, that's what I'm looking for. It's 0.
Ah, I see.
Okay, it's
Oh,
not
because
connected.
nothing's going to it.
Okay, all right, everybody. You see this when it says 40 on here?
That's when it's on.
That's only when it's on, and it does say,
It's not even always.
it says soft white bulb, 40 watts, 120 volts. So what's the only time this is a 40 watt bulb? When it's hooked up to 120 volt difference, potential difference, right? Okay, so here's the deal. A 40 watt bulb is not a 40 watt bulb unless it's hooked up properly. Right now it's a 0 watt bulb. If it was a 40 watt bulb all the time, it would be glowing in the package when you buy it, right?
Will it float over our heads? Put it on
Now-
your head.
I see the light.
See if it comes up.
Yes.
Oh, I was on the train downtown, and like I see this guy with like this weird hat, right? And he has a light bulb, and then he walks
That guy!
in the shade of a tower, and it's like glowing. I was like astonished. I was like, oh, what the heck?
Now, if we had followed Nikola Tesla's ideas, where he was the inventor of the Tesla coil, which bears his name, and also the lot of advancements in alternating current and the projection of energy through electromagnetic waves, okay? We thank Tesla for his Tesla coil because it helps us with things like this. All wireless communication for our phones and all that stuff uses a Tesla coil inside. And what his idea was is that you would not run wires to your house, okay? What you would do is you'd just set up this great big huge Tesla coil in the middle of the town, and it would send out such high amounts of energy that the bulbs literally would glow without having to be plugged in.
Is that safe?
So there's a famous picture of him sitting in a chair holding a bulb in his hand, and the bulb's glowing.
Is it safe though?
In the cage.
Sort of. Sure, it's safe. What's that?
And you also glow, and you have a little like metal wire on your head.
Yeah, if you had a little metal wire on your head would glow. Yeah, the problem with that idea is that then, you're sending out tremendous amounts of energy just out,
And
right?
just waste it.
would be wasted.
Yeah, a lot of it's wasted. When you send it on a wire, at least it's directed where you want it to go, okay? All right. So, 40 watt bulb, everybody. 40 watt bulb and 120 volts when it's hooked up properly. Okay, everybody?
Yes.
Pay attention because this is important. You won't get bulbs right unless you do this. That's the power. That's the delta V it's supposed to have. That's the design. Delta V. All right? If that's the design delta V, potential difference, and that's the power it's supposed to produce at design, okay? Then tell me what other things can we find out about this bulb? We can find out the design current, and we can find out the resistance inside. Okay, so you do that for me, please. Find the current that it should have when it's operating as designed, and find out the resistance. Okay? How are we going to do that?
40 over 135.
Okay, because power equals IV, so power is 40 watts, I, and that's 120. So what's my current?
Humbug.
0. Point what? 0.3, is that right?
Yeah.
Okay, 0.3 amps.
40 over 0.09.
So 300 minutes.
So 40 over 0.09.
So 330 people.
All right, so power equals V squared over R, right? 40 watt 120 volts squared over R. So R equals 120 squared over 40, which is,
A number.
it's a number. It's going to be a big number.
Not that big.
Huge.
Is it 360 or is it 240?
360.
360? Okay, 360 ohms. Okay? Okay, now here's the critical part to understanding bulbs. There's two critical things you really need to understand. Number one is, okay, when I hold this thing up like this, how many watt bulb is it? 0 watt bulb. So, when it's in the package, it's a 0 watt bulb. Why is it a 0 watt bulb?
Potential difference.
Because the potential difference it's hooked up to is 0. Therefore, it has 0 current in it. And so is its resistance also 0?
No.
Ooh, why not?
Because it's a resistance.
Because the resistance equals rho L over cross-sectional area, which should be 360 ohms for us, right? Okay, now this is a critical thing about bulbs. When we have a bulb, and you put a bulb in a circuit, we don't really care what the power is. We don't really care what the design voltage, the design power, and the design current is. The only thing that we know about this bulb for sure is always going to be what?
360 ohms.
That it's a resistor of this many ohms if it's a 40 watt, 120 volt bulb. Okay? So, when you have a bulb in a circuit, the very first thing you should do, if it asks you anything about the current, or anything about, the voltage difference across the bulbs, or anything like that, the very first thing you should always do is figure out what the heck it really is. It's a resistor of 360. At least this one is, right? So, if you have a problem that goes like this, and it's got a bulb, and another bulb, and another bulb, the first thing you do is you convert these into resistors, or at least write down what the resistance really is, because that's how you're going to solve the circuit. Okay? So that's number one. Number two is, there's going to be a lot of questions about bulbs. Whenever there's a bulb and a problem, the question usually has something about the brightness of the bulb or the power of the bulb. If this is a 40 watt bulb and they ask, well, what's the power of the bulb when it's operating? Everybody wants to say, well, it's 40. But it's only 40 if you hook it up to this many volts. If I hook these 3 bulbs in here to 120 volts, is that really going to be a 40 watt bulb?
No.
Why not?
Because there's more resistance to the current.
Yeah, because when we color our circuit, notice this is the high volt area there. And I just got random colors here. This is the low volts here. So only from here to here is it 120 volts. This bulb does not have 120 volts, so it will not be a 40 watt bulb. So if it's not a 40 watt bulb, what does that mean for its brightness?
Less than what it is.
It'll be less, right? Okay. If you hook this up to more than 120 volts,
It goes up.
it'll be brighter, right? So, the power consumption or conversion of the bulb from electrical energy into light energy. The more wattage the bulb, the brighter it will be because the faster it's consuming electrical energy and turning it into light energy. So, the higher the current or the higher the voltage, the higher the power will be. Okay?
Wattage. Is that a word?
Yeah. Higher wattage bulb. That's correct.
Cottage. Just made me think of cheese.
The higher the wattage, the brighter the bulb.
And so power equals I squared R or V squared over R. It's usually easiest if they ask you in a problem, which is the brightest bulb or something like that. Just go through and figure out, you know the resistance of the bulb. You'll calculate that, and then just find out which one has the highest current, which one has the highest voltage, right? Okay. All right, so let me show you a couple demonstrations back here of bulbs in circuits.
Can we stand up and watch?
Yes, you may. We'll start off with parallel. Okay, I'll tell you what, let's sit around this way, or come around this way so the camera can see. And will you close the door?
Me too.
And turn the lights
It's
on.
working good.
Really? Because I checked, she was.
Ooh. All right, it's very bright.
I see the light.
Okay,
Don't walk into the light. What?
this is hooked up in parallel. Okay, when they're hooked up in parallel, if I disconnect this one, what's going to happen?
Nothing.
The others may stay parallel. Yeah.
Well, something will happen.
Get
First of all, my fingers will burn.
Get
The
bright.
second thing is that that one will go out, right?
Oh.
But does anything happen to those at all? Nothing, right? Okay, when they're in parallel, remember, Al, okay, that when they're in parallel, the voltage from the switch here, it comes around and they all get the 120 volts.
It's the
When I
same
disconnect one,
resistance, so same brightness.
yeah, they have the same potential difference, the same resistance, so therefore the same current, therefore the same brightness. Everything's the same. All right, hand me the little bitty one down there. The cute little one. All right,
Who has a dim?
it does have a dimmer.
Fancy.
It's fun.
Oh, you fancy.
Fancy Nancy. It's hot.
Wait, when you execute yourself, what happens? Does your hand just sweat? Does it mean your hand doesn't burn up? Does it?
Okay, here we go. First of all, I got a dimmer switch on here. A dimmer switch is a resistor in series with the rest of the circuit. And what it is I'm just changing the amount of resistance. Changing the amount of resistance changes the amount of current that goes through. All right, now look. These are the same 40-watt bulbs that we had over here. Why not so bright?
Because
They're in
they are.
series, so net resistance is great.
All right. There's a couple of reasons. Number one is you could say, look, when they're in series, the overall resistance of the circuit goes up, therefore the overall current of the circuit goes down, therefore they have less current than they had before, so they got to be dimmer, right? Less power. You could also say that, well, I have 120 volts coming out here, but this one doesn't consume all 120. Watch out, don't fall. It's scary. Lights go down, everybody goes crazy.
Raving time.
Brilliant people.
All right, so now, this one only gets half, ow. This one only gets half the voltage, right? Half the voltage. Now wait a minute. Half the voltage. Half the voltage. Power equals I times V, right? So half the voltage, does that mean half the power?
Yes. Yeah.
Fair enough.
Seems that way, right? But
But
the current changes as well because the total resistance goes up, right? Okay, so let's back off. What stays the same about this bulb when I moved it from here to here?
The resistance.
Resistance. Okay, what's the power equation that has power in it and resistance in V? V squared over R. Now wait a minute, the voltage gets cut in half, right?
yeah.
So voltage squared over the same resistance. So it's 1/4 the power, therefore approximately 1/4 the brightness.
But
Okay.
resistance is twice, right?
Yeah, what happens is the total resistance has been doubled, so the current gets cut in half, and the voltage across this one is cut in half, so again, you get 1/4. No. So if you look at P equals IV, you get 1/2 the current and the voltage, so therefore half the power. If you look at P equals V squared over R, you get 1/2 the voltage but the same resistance, so you get 1/4. If you look at P equals I squared R, you get half the current but the same resistance, so you still get 1/4. So any one of those you look at, you should get 1/4, okay? All right, now, what if I take one of these bulbs out now? Okay, they all go out, right?
Oh.
They all go. Oh, because that's series, right? Okay. Now, give me the last one, please. Thank you.
Lauren, where's your hand?
Okay, this is a combo circuit.
It's not chance.
Oh, that is so cool.
We turned it off because we didn't want to.
Give it away just here.
Can I have it?
Can you have it? You can make one.
have that kind of
That's why our
stuff at home.
country is in shape.
And that means joules per second.
Okay, okay, let's turn the lights on real quick. I'm gonna ask you to predict in advance the brightest to dimmest bulb, okay?
You don't know how they're
The
connected?
brightest is the one closest to it, the dimmest is like the one at last connected.
You just
How are they
make
No,
it-
no, no, just because these were all closest and farthest away.
But how are they connected?
Okay, how are they connected? All right, let me draw back there, I need a marker.
I think these two are in series parallel with that. Series with that. That's fine.
All right, let me draw it back here.
Maybe
That's what happened once with my back.
Okay, here's the circuit. It looks like this. Power. We've got a bulb here. We've got a bulb here. And we've got a bulb here and here. Okay, that's how it's set up, and there's a switch right here. Okay?
Obviously, this one's supposed to be the brightest.
Obviously.
Yes.
Okay, we're going to call this one bulb A,
I think maybe
B,
people have the same brightness.
C, and D. Okay, think about it. Rank them in order. Talk to your neighbor.
A1, D2, C, and D.
Wait, what order do you want them in?
Brightest to dimmest.
A is brightest,
Then
then
B,
B,
because they'll
then
have
C,
more
B,
current.
and
A, B, C, D.
You each have for B.
And C and D will go on.
A, B, C, D.
Because they're parallel.
one.
They're parallel.
Yeah, A is the brightest.
Why is A the brightest?
Because
they
it
have
has
Straight
current.
to it.
Because this is the total current. Total current, so it's going to have the maximum current, so V squared, oh, sorry. I squared R for power. It's got this, all these bulbs have the same resistance, but this one's got all the current. Okay, now, what about these?
So these could be more current through B.
They're both
Why more current through B?
Less resistance.
Okay, we have less resistance in this line than this line, and they have the exact same voltage difference here and here, right? Okay, so this one should be, well, this current through B should be bigger than the current through here. So A should be the brightest, B should be next. What about C and D?
They're the same.
C and D should be the same. Why?
Same current.
Why?
Because they're in series.
Because they're in series. Series, same current.
I told you it would be wrong.
It would be obvious. Oh, I can't see a thing.
Go, Mr. Bowles, go.
Shiny bulb
Yeah. Use a light bulb. All right, there you go. You can't tell nothing.
You can see the brightest,
Okay,
second
brightest.
those two, you can't tell.
Second brightest.
No, they're on. You can see them.
Okay, I need a, here. This hopefully won't catch on fire.
Yeah, they're on.
Okay, that one's on, right?
Those are.
Can you see these?
Yeah.
You can see the little.
Do you see the little wires? The little wires inside are glowing. All right?
Rudy, you're crazy.
It should be okay. All right, now, tell me this. If I remove bulb A, this bulb right here, what happens?
They all go
They'll
out.
go out.
Oh, I don't believe it.
No,
I believe.
they're gonna get slightly brighter.
Really, Daniel?
Why do they all go out?
Because it's in series.
Oh, yeah.
Because it's in series with the rest of the circuit. Okay, now, what if I remove bulb B?
Those two will get brighter.
Yeah.
Yeah, those two.
Oh wait, no, wait, yeah.
Yeah,
Yeah,
they will
yeah.
get brighter.
The last
Those
two
in
would
series
get brighter.
without.
Nothing would happen. No, would, yeah, current, the last two would get brighter.
Okay, think about it for a
Wait, hold up,
second.
no,
Wait,
wait,
no,
but
he's
then
right.
resistance
He's right.
would be different.
It would go through. So go through the. Yeah.
Yeah, they would
Okay,
get brighter.
turn on the lights for a second. Let me come back here.
Because that one would go back.
Turn that off so fast.
And AC and D would have the same current.
Okay, when we have a combo series like, combo circuit like this,
It breaks the current breaks the circuit.
It would be the same.
The other one is that.
so this is my new circuit. Now, please be careful. When I undo this bulb, I now go from a combo circuit to series. So tell me about these three bulbs.
No, the
First rule
They
goes
all have to be the same.
And
The first one
the
goes
first
in,
one's
but
gonna
the
get
other one
brighter.
will get brighter.
And those are gonna get brighter.
All right, now, what happens to the total resistance of the circuit when I take that one out?
It goes up.
Why does it have to go up? I'm taking the resistor out.
Just add parallel.
Because it gives it fewer ways to go through.
All right,
But keep in mind, net resistance.
It makes the entire thing in
Make
circuit.
sure-
right here, everybody.
Yeah,
Look.
serious.
Look. Okay, right here, when you have this in parallel with this set, whenever you add a parallel line, you lower the overall resistance of the circuit, right? So when I take this line out, there's less places for that current to go around, right? So therefore, the overall resistance total of the circuit has gone up. Therefore, the total current of the circuit should go down. Therefore, what happens to this brightness?
It goes down.
This brightness goes down, these two brightnesses should go up. All right, trip. Sorry. All right, let's try it. You ready?
Yeah.
Now these bulbs are not all the same exact bulb. This one's an older bulb, so they should be the same brightness. Let me take this one out and replace it with the other one, and you'll see that they are the same brightness. What's that? There, now you see? They're all exactly the same brightness? Excellent. Okay, now riddle me this. What if I take out bulb C?
B and D will be the same.
The center one will go brighter, and the last two will go out.
Just, well, that one will go out with the
Oh, take that out in addition.
Oh.
Because it's in series.
The heck?
Hang on, I'm rearranging. I got this one crud bulb here, so I'm getting
Well, we
rid of
already
it.
know now.
All right, I know. All right, okay, so I take out this one. Voila. Now, wait a minute. Those two are brighter than when I take the center one out.
Yeah.
Why?
Because there's three.
Resistance.
Because this has 3 resistors in series,
No, no, no.
and this only has 2 resistors in series, right?
Yes.
It's pretty cool. All right, if you understand that, then you are in pretty great shape for bulbs. The only thing left for bulbs is if you have to calculate some numbers. So let's do a little bit on the board with numbers.
I'm not a big fan of puzzles, I think I chalked it up.
But then you get thirsty.
I like soft drinks. You want to bring me a soft drink?
What has iron in it? What kind of food has iron in it?
Oh yeah, beans. Bananas have potassium, that's what they did to super most people get tired. They make you get bananas.
Okay, that makes sense.
That way you don't get tired. I remember my coach tried a bunch of bananas and I was like, why is it so
Okay, everybody, here we go. We're going to start with this one right here. I've got a 120 volt potential difference, EMF.
More dangerous.
I'm going to hook it up to a 40 watt and 100 watt bulb in parallel. Okay, when I do that, which one's brighter and what are the wattages of the bulbs?
Wait, what are you talking about?
This is a normal
Oh, okay.
40 watt bulb when it's hooked up to 120. And then I've got a, ready bulb. I got a 100 watt bulb, 120 volt. I'm going to plug that one in here and plug that one in here. And I want to know when I plug them in, which one's brighter
No, 100 watt one.
and what are the actual wattages of the bulbs?
Well, assuming there's no internal resistance, there's none.
Assume no internal resistance of the battery.
Actual thing.
Then that's going to be a 40 watt and a 100 watt bulb, and the 100 watt bulb's going to be brighter, right?
Yeah.
Yeah.
Because that's the way we actually hook them up, right?
Yeah.
We're supposed
Okay.
to, yes.
That's the way we would normally hook them up in a house or whatever, and that's how they would look. Okay, now I take that 40 watt bulb, plug it in here, and the 100 watt bulb and plug it in here, and I want to know which one's brighter and what are the actual wattages of the bulbs.
No, wouldn't the 100 a little bit brighter than the
Let's find out. Okay, what's the very first thing we should do when we have them not hooked up as the way they're designed to be hooked up?
Find the.
Make sure you don't burn out.
Check the net resistance, I guess. Would be something.
Okay, we got to find the resistance of these bulbs, right? So we already know what the real resistance of this bulb is, right?
We do.
What is it? 3 360 ohms. We already calculated that one, right? Okay, everybody calculate what is the resistance of our 100-watt bulb?
120 squared.
Okay, because power equals V squared over R. 100 watts equals 120 volts squared over R. So R equals 120 squared over 100.
Which was 144.
144 ohms. So this
Has less resistance.
becomes a 144 ohm bulb. All right, now, I want to know which one's brighter. Actually, let's not worry about brightness at the moment. What will the power of each of these bulbs be?
Not what it says on the bulb, I can tell you that.
Yeah.
Equals IV.
Certainly not what it says on the bulb, right?
Well, first of all, you know the voltage across both the resistors is equal to 120. You can say that.
Okay, we know the voltage from the 360 plus the voltage over the 144 must add up to be 120 volts, right? We know that. What else do we know about series? Yeah, the current through the 360 equals the current through the 144. Okay? What else do we know about this circuit?
The voltage. Oh, I said that. Total resistance.
We know the total resistance. The resistance total equals
500 and some more. 504.
504. 504 ohms. Wait a minute, if we know the total resistance, that means this becomes this circuit, right?
Yes.
120 volts and 504 ohms. So can we figure out the total current?
Yes.
What is it?
120 over 504.
120 volts over 504 ohms. So what is that?
238 .095 milliamp.
What is it?
Intro. 0.238.
0.238 amps.
I gotta try to do it in the intro. 238 milliamps.
Now you could say 238 milliamps. If you want to say 238 milliamps, just make sure you put your units on it, or they won't count it right. Because it's not in standard
We've been
units.
start for life.
Yeah.
It's okay.
I know, you get it wrong.
Yeah.
Wait a minute.
You get the whole question wrong if you don't put it in milliamps.
Yes.
Wait, on the physics test? That's how it is?
No, on the physics test, if
You just get
most of the time now on the test, if you don't put units on your answer, you don't get the answer point.
you just get the whole question.
Now you'll get oh no, they're not that bad.
It's 20
It is
points
like
off.
it, though.
Yikes. All right, here we go. Now, how do I figure out power? Do I have enough information to find out power here?
Oh, wait, that is. Hold on.
Yes.
I need either IV, I squared R, or V squared over R. Which of those do I
You
know?
have all of them.
You have
Well,
we don't have voltage at each specific.
I don't know the voltage across that, do I?
But you know the whole voltage.
But that's not the same as the voltage for this one.
So you know I squared and no.
Okay, everybody, this is really important because it's very common for students to do this. It's common for almost everybody to do it at first. I'm looking for the power of the 144 ohm resistor. That means I had to use the current through the 144 ohm resistor and the voltage of the 144 ohm resistor. That's not the same as 120, right? That's only from here to here. Not from here all the way around to here, right? Does that make sense? Okay, so which of these do I know? I don't know the voltage.
So you use I squared R?
But I do know I squared R. I know that it's 0.238 amps squared times 144 ohms. So what's my power?
8.157.
8.16 watts. Holy cow! My 100-watt bulb has become a 8-watt bulb. That's a night light.
Not even.
Well, that's about a night light. A lot of those night lights are like 7-watt bulbs.
My girlfriend has a night light. She's 6, 7.
How would you know?
Oh.
We're gonna show this tape.
Back to physics. Back to physics.
He did her electricity, that's why.
You wired up?
Yes.
All right, very good.
Thank you.
Nice boyfriend thing to
It
do.
was a gift for her. That's it.
All right. All right, we're just going to move forward and pretend this never happened. Okay, what's the power of this one, everybody?
Stop! The answer. She messed it up. Wait, what are we doing?
What's the power of this bulb?
20 times? No.
Just-
Times 360.
20.39.
So I get 0.238 amps squared times 360 ohms, and I get what?
That's meaning.
20.39.
20.4-ish, right?
4-ish.
392.
Whoa, that's a 20-watt bulb. So wait a minute. This was a 40-watt bulb. So its wattage got cut in half. It's now a 20-watt bulb. This is my 100-watt bulb. It's turned into an 8-watt bulb.
I got cut by 12.
Hey, that's really weird, everybody. Look, that means that when I plug in a 40-watt bulb and a 100-watt bulb, the 40-watt bulb is going to be
Brighter.
nearly 3 times as bright.
Because it's hooked up.
Because it has a higher
Because it has a
Okay, not because it's hooked up first. I could flip them around. They'd be exactly the
They're
same.
the same.
higher voltage drop.
And in the parallel, they're not the same because there's more in the other one.
There's a
because
greater
there's less
resistance on that one.
Okay, here's the deal. This is confusing for students sometimes, but look what happens here. This device has a high resistance, higher than this one, right? But we know that the current through both of these devices must be the same. The only way for this current and this current to be the same is for these to be the same ratio, right? This one has a high voltage drop. This one has a low voltage drop so that they have the same ratio for the same current. Okay?
They do have the same.
They absolutely do.
Power resistance ratio is the same.
Right, and you can think of it this way too. How is it possible for me to push the same current through this big resistor as this small resistor? The only way to push the same current through a big resistor is to give it more potential difference, right? More voltage to push the current through. So when the voltage gets bigger here, you end up with a brighter bulb. Okay? Counterintuitive. Okay? Very counterintuitive. Okay, so let me ask you this one. If I had 3 bulbs, all 3 bulbs are the same,
This is making fun of your bulb.
Megamind's head.
how would I hook up these 3 bulbs
Megamind's head.
to produce the most
Daddy
brightness?
should make up my head.
Why?
Wait, what? To produce the most brightness? Parallel.
How would I hook up these 3 bulbs to produce the maximum brightness?
In parallel? All of them in parallel.
Yeah.
To each other, in parallel with a voltage source.
Because if I hook them all up in parallel, they'll all get the maximum voltage,
And
therefore they'll get their maximum brightness, right?
Yeah.
Okay, there's another way to think about this too. When I hook up 3 resistors in series, what happens to the total resistance?
it's
Goes
a lot.
three times whatever.
Resistance
each one
goes
is.
up. It's 3 times the original, right? But what happens when I hook up 3 resistors
They're
in
less,
parallel?
they're
It's
less
1/3.
than each
I believe.
one.
Yeah, this resistance gets tripled. This resistance
1/3 of
gets
one.
cut.
Of one of them.
Yeah, 1/3 of one of the
So
resistors.
it's a 9 times difference.
All right? And when do you get maximum power, everybody? When resistance is high or low?
High.
Low.
High. I squared R? Low.
Low.
Power, well, it depends on what you're doing.
Power equals IV, I squared R,
Oh, yeah.
V squared over R.
So you want the small
Now remember, you want a high current and a high voltage, right?
small resistance.
But you want a low resistance here, and you want a low resistance here, because remember, if you have a high resistance, that cuts your current, right?
Oh.
Right? So you have to have a low resistance so your current is bigger, because current is more important than resistance for power, right? So you want the lowest resistance possible. So let's say I wanted to heat up this room. It was a cold day, like remember the ice storm is supposed to hit tomorrow, right?
Oh my gosh, it'd be freezing, like in the zeros.
Yeah, it's going to be like in the teens, I think.
Is it gonna snow?
There's a 100% chance of precipitation.
No. Oh.
120% chance. That means we're going to get 20% extra snow. All right, now listen. Hey, I want to heat the room up because it's cold. I have 3 resistors and I want to heat the room up. How do I hook up the resistors so that I get maximum heat? Hook them up in parallel.
Alright.
It parallel produces maximum, it produces lowest resistance, therefore maximum current, therefore maximum power. Okay. Now, let's talk about, that's bulbs, by the way. You all done with bulbs?
I get
You
it.
all done with bulbs?
We're done with bulbs.
We are.
Okay, first of all, let's talk about how capacitors work.
Capacitate.
All right, shh, you gotta take notes. Notes. Okay, capacitor. A capacitor is 2 conductors separated by an insulator. So it is a disconnection in the circuit. Okay, did everybody catch that? Hey, yeah, I got to switch. Okay, everybody, shh. I know some of you are working on your homework. You need to set it aside for a second. We're talking capacitors, all right? Something new. And you need it. All right. The capacitor is not a complete circuit device. When you put a capacitor in a circuit, it's a disconnection. That means for direct current, what we're talking about here, current flowing in one direction all the time, current cannot flow through this indefinitely. It will eventually stop all the current. Now, it doesn't stop all the current instantaneously, because what happens when you throw this switch, remember this is negative and this is positive. So what happens is that charge begins to flow because of the difference in potential. And so, okay, we all know positives don't really move through solids, but we will assume positives will flow this way and this way. Okay, simultaneously. Adding charge here and subtracting charge over here at an equal rate. So this thing begins to fill up. When is it full? That's not an appropriate physics answer.
When it reaches.
Charge flows until when?
Until potential difference is the same.
Okay, until equilibrium, and equilibrium is when the potential difference between the two sides.
No, it's 0. Potential difference is 0.
Here's what happens. You see this side right here, it starts off at no potential, but this is high potential here, right? So charge shares from here to here until this potential on this side is the same as this side of the battery. And this side of the battery, the negative side of the battery, shares potential with this plate because it started off at 0, right? Until this plate has the same potential as this side. Now that's equivalent to saying, when does the capacitor fill up? Whenever it matches the potential difference it's connected to. Does that make sense? So whenever the capacitor gets to the same potential as whatever you hook it to, then it quits. All current ceases. And in fact, you'll learn when you get to Physics C that the current will flow onto this thing. It'll have a maximum current, and then it'll eventually die out to 0. And the voltage of this thing will start off at 0, and it'll eventually reach equilibrium. And these are asymptotic approaches. Okay? They'll start real fast, and then eventually they'll reach their equilibrium. Because it gets harder and harder to shove these charges on there once the thing starts to fill up, right? So it slows down until it eventually quits. All right? And when it quits, it stops. No more current. Current ceases. So at the beginning, it acts as if current's flowing through the capacitor, when really none has ever flown through it, right? All right. So there you go.
Okay, but if you close the switch, the
Okay.
potential difference is continuously existing.
When you first close the switch, you had high potential here and low potential here, but nothing else. And then when you close the switch, then the charge flows until that thing charges up the same potential as the battery.
Yeah, but what I'm saying, like, I mean, when we were doing capacitors earlier, didn't we say if we have it continually, if it's constantly connected to the potential difference source, then the charge has to flow, doesn't it?
Charge flows until it reaches equilibrium, and then it quits.
But if the potential difference is existent because it's
Yeah.
battery,
But eventually this, like if this is 9 volts on this side and 0 volts on this side, when this reaches 9 volts, it can't shove any more on. It has to quit,
alright.
okay? It has to stop. And once this reaches 0, no more can flow this way. So it stops. Now, here's the cool thing you can do with a capacitor then. You can disconnect it. Okay? You can disconnect it and walk around with it and set it on the shelf, then pick it up later, and it's still got this charge. Now, in the real world capacitors, they will eventually drain out because they'll bleed, a little bit of the charge will bleed across through the middle, or it'll bleed off to the atmosphere or something, right? But like in this type of TV set right here, there's a big capacitor inside. Okay? So if we were to turn off the TV, open up the back, and touch both sides of that capacitor, it would be a bad day. Because there would be a popping sound and we'd take you to the infirmary. Okay?
The infirmary, just lay down for a few minutes.
Lay still while we all run. Okay? It would hurt. Okay? But those things will slowly discharge. Like after a month or two, they'll be totally discharged. Okay? But in our imaginary physics world of Physics B, our capacitor will stay charged forever. Forever. Okay? Now, when will the capacitor ever discharge?
Never.
How do I discharge a capacitor?
By taking out the switch? I mean, opening the switch?
So like for instance, how could I discharge this thing?
Put a resistor. Something
Yeah.
that will work.
If I just connect the circuit, if I connect both sides, then what happens? High volts to low volts, and current will flow back this way. Okay? And current will flow back. So, what if I have a circuit like this? And I got a light bulb, and I got a capacitor, and I do this, and I have this switch, and I throw the switch shut. What's it going to do?
The question, positive flow there.
Charge will flow, but it'll start to build up.
The light bulb will get dimmer until it turns off.
Yeah, what happens is charge flows, the light bulb's all lit up, but as this thing builds up charge, eventually no more current. No more current, no more light bulb.
No more whatever.
No more glowing light bulb anyway, right? It'll go out.
Yeah, because it evaporates completely.
All right? Yeah, the bulb evaporates completely. That's correct. Hey, now what if we do one like this? Okay? And I throw the switch. Same thing.
The light bulb will.
At the very beginning, this thing has resistance, right?
It always has.
But what's the resistance of the capacitor at the very beginning?
Zero.
0, because it's got lots of room for the charge to flow on, right? So this acts like a short circuit.
Also just go ahead.
Yeah, so what happens is at the beginning, all the current goes this way. But then this thing starts to charge up, and then what
Slowly
happens?
builds up.
And then slowly the current here starts to die out, and then the current starts to go through here. So in this, it's just the opposite of this one. In this one, the light bulb's very bright, and then it dies out. This one, you throw the switch, nothing for the light bulb, and it slowly builds up. Okay, it is actually pretty cool. And then if this was like in your car, some of you are have a car or been in cars where you open up the door, the light goes on?
Yeah.
And then when you close the door, the light stays on and slowly dies out? Okay, look what happens here. I got this thing hooked up. I open my door, and when I open the door to the car, that's like throwing this switch. The switch closes. The light bulb comes on. And then I close my door. And when I close my door, the switch opens up. Now look what happens when the switch opens up.
The current goes from there to there.
Yeah, this switch is open, but now I have high volts here connected through this bulb, right?
Until it
And so current's going to flow through here. Until when?
So it goes in opposite direction?
Yeah. Well, through the bulb it continues to go the same direction, but it goes the opposite direction through here now. And so the bulb will stay lit. Until when?
until equilibrium of the capacitor.
Yeah, well the charge is going to come off and then eventually discharge the capacitor and it'll no more stored charge, right? So it'll slowly die out. So that's one way you could do that. Okay? That's one way you could design that so you open the door, light goes on, close the door, light slowly goes off. Okay?
That's pretty cool.
Alright, so if there is a connection from one side to the other, the capacitor will discharge. If there's no connection from one side to the other, there's no other way to get through, no other path, then, like if there's something like this, you disconnect this bulb won't go on. Right? So there's no way for the current to get through there, right? Whereas here, there's a complete pathway. Alright. Now, let's talk about, real briefly, a couple of things about capacitors. When this thing charges up, the left side in my drawing will get a charge of positive Q. The right side will get a charge of negative Q. These two Qs are the same. That means the net charge on a capacitor is always 0. Okay? So when we talk about the charge held in a capacitor, we're just going to talk about one plate. Because otherwise it always reads 0. Okay? If we add both together. Alright? Yes. Now, what if I increase the EMF here? What will that do? It'll shove more charge on, right? And it turns out that if you put more volts on, you get more charge on, and that always comes out to be a constant for a given capacitor. Okay?
They increase the same way.
Yes.
Different.
And that's our capacitance, which we already talked about, right? Q over V. We talked about static electricity already.
Yeah.
And what is our equation for capacitance again, for a parallel plate capacitor? You remember?
The charge on one times the area.
Alright, I got this.
Times the area over the charge times length. Oh, you just did? Ah, whatever.
Isn't that right? Okay. Okay. But how does that affect us when we're in circuits? Ooh, look, if we have a circuit, and what if we hook up our capacitors like this? In series.
Oh. The first one will take it all. At first.
Alright. Hey, everybody. This is series, right? In series you get the same current, right?
Yes.
But for a capacitor, that means they'll all have the same, not current, because current doesn't last forever, but the same charge. Same charge here, same charge here, same charge here, right? Alright. Okay?
So what would happen when the first one fills up?
Well, they'll all fill up simultaneously.
Do they? Because of the charge from one is leaning toward the other one.
Because when the current dies here, it has to die here and here. Okay?
So they all, and how would they all store this equivalent amount of charge?
Would it do the same thing?
Alright, so they will all have the exact same charge. They must have the same charge.
Are those capacitors? All those?
These are all capacitors, sorry. This is a battery. And then capacitor 1, capacitor 2, and capacitor 3. Okay, now let's apply Kirchhoff's Kirchhoff's other rule. The current rule tells us that all the current is the same. So therefore, they all have the same charge. But the voltages go like this. The total voltage equals the voltage of capacitor 1 plus the voltage of capacitor 2 plus the voltage... Wait. Back up. As you go around the loop, the sum of the voltages add up to 0, right?
Yes.
In the voltage rule. Well, what do I get? I have my EMF here, right? And that has to have a voltage drop across here then, right? This adds volts.
Yeah.
This will consume volts, and consume volts, and consume volts, right? So I'm going to have a minus delta V for capacitor 1, minus a delta V for capacitor 2, minus a delta V for capacitor 3. And that should all add up to 0, right?
Or they're equal.
Okay, and I'm going to rearrange that. So the EMF equals delta V capacitor 1
Plus.
plus delta V capacitor 2 plus delta V capacitor 3. Everybody okay with that?
Yep.
Yeah.
Dead zombies.
Okay, you could call this the total voltage, right? If you want. But right over here, look at this. How do I find delta V for a capacitor? You see this? That's C equals Q over delta V, or delta V equals Q over C, right? So I'm going to take that and plug it in for each one. So I'm going to get Q over C plus Q2 over C2 plus Q3 over C3. Ooh, you all ready? Do you see it?
Yeah.
It's all the same.
All the Q's are the same.
And all the capacitance.
So that's the same as Q times 1 over C1 plus 1 over C2 plus 1 over C3. So what's that? The equivalent capacitance in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. The equivalent capacitance. That's the capacitance of all three of them in series. Hey, now everybody, that's just the opposite of resistors, right?
Yeah.
And then parallel the opposite.
Yes, so guess what? Capacitors in parallel add up by adding up.
LOL. So wait, are they Siemens?
Yes.
Yes, conductance.
Yes.
Oh yeah.
Okay, so real quick, let's do one. What if I had a system of capacitors like this? Okay, let's say that this is 1 microfarad, this is 2 microfarads, this is 3 microfarads, and this is 4 microfarads. Okay, what's the total, not farads, what is the total capacitance of this setup?
You said 1 micro.
Excuse me. It's 0.78.
Wait, so what? The ones that are in series are 1 over.
Ugly. Ugly answer.
787.787. I mean, no,
Wait.
Okay, when you add those two up, when you add those two up, it's 1 over 3 plus 1 over 4 equals 1 over the capacitance total for what we have here, or capacitance in series. So that turns out to be,
A really weird number.
yeah, a strange number.
And then you add 2.
Is that 1.7? Is that right? So this becomes 1.7 microfarads, and then I add that
to 2.
to 2, right? And those are in parallel, right? So I just add them together. So that set becomes 3.7 microfarads. And then that and that are in series, right?
Yeah.
So I get 1 over 3.7 plus 1 over 1 equals 1 over the total. And when you invert that, the total capacitance is 0.78 repeating. Sorry, thank you, microfarad. I got that wrong. I got that wrong. All right, so there you go for capacitors in circuits. Now, everybody, remember, how much power is stored in a capacitor? We learned that one earlier. Sorry, not power. How much potential energy?
1/2 CV squared or QC.
1/2 what? QV equals 1/2 CV squared, right? Now, here you go, everybody. It's a really easy problem if they do this. And they say, okay, they hook it up to a battery, they give you what the capacitance is, and so you know the delta V because it's the same as this, right? Piece of cake. So you can plug it in and find it. Okay, but what if they give you a problem like this? What if they give you this? All right, everybody. I want to figure out, they'll usually say something like this. They'll usually ask you a problem about this part of the circuit because the switch will be open. Then they'll say, now the switch is closed. After a long period of time, what does that mean? Long enough time for this to get charged totally up, right? And no more current to flow through it. Okay, so this switch is closed. It says after a long period of time, what is the energy, potential energy of the capacitor? Okay, well, no problem. Potential energy is 1/2 QV, which is 1/2 CV squared. We know what the capacitance is. We just have to find the voltage difference, right? And use this one right here.
Voltage difference equal to whatever it is over there.
Ah, now that's the trick.
Oh, no, there's a 6 ohm resistance.
Is the voltage difference here 12?
No.
No, because there is
12
12.
minus the 6 ohm. Whatever the 6 ohm. Ooh, that's good.
Okay, it's going to be whatever yellow to purple is, right?
Yellow.
Which is the same as the potential difference across this resistor. That's important.
So can you do like
Yeah, so what you'll do is you'll just forget about this for a second, figure out the current through here, and figure out the potential difference here, and then whatever you get here, that's the voltage you put in there. Not that bad, you just got to know that that's what you do. Now what if there was another resistor right here? Would we worry about this resistor?
no, it's in series. So
It's in series with this capacitor, therefore, once this is charged up, there's no current through this resistor, right? Therefore, there cannot be a potential difference across it. It's like it's not even there. It doesn't do anything. Okay?
Wait, what? What was that?
If there's no current through here anymore, once this gets charged up, then it's got to be purple on both sides. Because if it was some other color in purple, then it would go through, right?
If it was purple on both sides there, then it's purple on both sides there, and purple, just the same color all over.
Yeah, then no current.
Nowhere at all.
Nowhere at all. Okay, that's capacitors. And I think I answered your question for capacitors on your e-homework.